Hi students, welcome to another very exciting session of mechanical characterization and modeling of tissues. So today we will get started on the different kinds of mechanical testing methods which are available in the market. So far we have especially talked about the different soft tissues and on a broader terms what the different mechanical characterization techniques are and the properties are of different soft tissues. We have also so far compared the soft tissues, how their property lie, whether they're very stiff versus medium stiffness versus very low stiffness, right? So let's take a closer look into the different mechanical characterization techniques which are out there in the market, and then we will slowly get into some of the examples of how this testing is conducted, right? So let's get started. All right. So the first type of tests and which are considered to be fairly reliable in the world of mechanical characterization is in vivo tests. In vivo specifically means when you are doing something on a live system. Live system as in like a live animal model or a live human model where you're doing certain types of testing. So you can well imagine by the term itself that you cannot be testing everything, like you cannot be poking inside a brain or you cannot be poking inside several other components of the body just like that, right? That has a lot of ethical and biosafety implications, right? So that's why in vivo tests, uh, even though they are very well done, like, but they are not super popular in terms of characterizing the mechanical property of soft tissues. But nevertheless, it's worth the mention to look at like some of the important ones, like which are out there. So the first one here is indentation test, which is basically historically that's how tests are conducted, where basically you are looking at the human skin, for example, that is the soft tissue which is undergoing the maximum number of in vivo indentation tests. So you see on the figure on the left, a part, a hand, a human hand, and basically there is an indenter. So basically this arm is like placed in a particular location, and of course it could be you could put a velcro or something to just make sure this is not moving or rotating, so that it is in place, or there could be a plaster cast to just put the arm in place so that there is some clamping. And then you have the indenter, which comes close and takes a little bit of dig, just kind of pokes onto it but doesn't really penetrate. So the indenter doesn't penetrate but just pushes onto the skin and tries to take a dynamic measurement. So the measurement is something which you look at into the plot here. So you're reading load force in newtons along the y-axis, and you're looking at the penetration depth in millimeters along the x-axis. So you could well imagine this penetration depth is 0 to 1 millimeters. That is very small, right? So you're taking a very small amount of push with the indenter to understand the mechanical properties of the tissues. But on the downside, what happens is, look at the load forces. You're looking at 0 to 0.02 newtons, which is a very small amount of force. That is typically what is happening due to the small amount of displacement, right? So the point here is, this may be good for having said that, like, it's an in vivo test, but is it comparable to real scenarios where your skin can be subjected to much more greater loads and which can cause much more greater deformation or displacements, right? Is this all scalable? As we have seen quite well, the soft tissues, when you keep on increasing the load, it has a non-linear profile, so you may not be able to scale what you see at this scale in vivo tests to a real scenario. So that is one of the shortcoming of these kind of tests, but they're done quite widely in the research arena, right? So on the right side, you're looking at another indentation test where basically it shows this schematic where there is a liver specimen. So it is trying to do an indentation test on the liver specimen, on a live liver, right? And that basically has an indenter with a clamp and some low friction copper sleeves. The indenter, the head of the indenter is of like interest, because that's something which is designed in a particular way. You cannot just have like a V-shaped indenter or a certain round shape indenter. It is well calculated what the circumference would be, what the like radius would be and whatnot like of the indenter, and as per that you are predicting a certain type of test. So if you change the head of the indenter, it may give a very different solution, right? Because that's how it is poking on the skin. If it is a flat surface versus a curved surface, it has a very different kind of load response, right? So as this is done, a 3D scanner scans the coordinate which is connected with this indenter. So it's very high precision measurement which takes displacements in the order of less than a millimeters, right? And you're measuring forces much less than a Newton. So typically while this scanning is being performed, you're seeing this pictures on the bottom where you're trying to see the poke of the indenter, which is circular here. You're looking at a 4 millimeters of radius if you were to look at the entire area, but it's much smaller than that, right? And then you kind of look through that area and see how that area is like. Is it completely round or completely like a little oval? Based on that, you say take certain decisions about the soft tissue properties, right? So the lever on the 10 millimeter scale is placed on the figure on the right, B and C. That is the poking of the lever, how this is shown. Sometimes in vivo tests, even though they have to be done in the live models, they are sometimes done in a little bit in vitro fashion where there are simulants or like some tissue engineered material which they are calling liver, like it's an engineered tissue engineered liver, and then you poke on it and you call it an in vivo. That is not entirely an in vivo. In vivo actually means if somebody is testing on me for taking the properties of the skin or liver or something else. Majority of the organs it's not possible. It's mainly done for the skin, right? Let's go further. So this is where the in vivo tests have come. They have been started to be done like on simulants. Simulants is a very broader term, and I'm going to take quite a bit of interesting sessions on the simulants, how to develop different kinds of soft tissues which can mimic the mechanical properties of the native tissue or the real tissue as closely as possible, and that's quite often used for all sorts of surgical tests as well as mechanical tests, right? So simulants have been recently very popular because in vivo tests per se, like within the human body, if you're trying to poke the brain, that's just not possible, right? It's totally unethical if you just have somebody sit and you want to poke the brain. That can cause different kinds of injuries, right? So this is a typical indentation test where you're looking at let's take a look at the figure on the left. You're looking at a force generator, force transducer, almost looks like a needle, like a syringe. Then you're looking at a distance transducer. So within the syringe itself, you have a lot of micromechanical devices which are packed. Micromechanical are they're small size, they're mechanical, and they have an electronic component to itself. Then there is a magnet. Then you have finally skin, and then you have the part of the tissue under test. So you can poke this needle, and this is not an entirely a penetrating needle per se. It has a little bit of blunt end, so which can take the same measurements. It will basically cause a displacement and measure the load dynamically for a small range like 0 to 1 millimeters, let's say. So there are different types of needles like probe assemblies. We are not calling them needles per se, they're probes. So you're looking at the figure B where basically this person is trying to poke into a material simulant which is a mimic for the brain tissue, and he is basically trying to see, as the computer records the force versus displacement, he's trying to do that precision poking. Sometimes if you are using your hand for poking, it may have some 1 millimeter is nothing, right? Like I will not even realize when I've moved my arm 1 millimeter. Sometimes that's why it's nicer to have some clamps or fixtures where you can place this indenter, and this can have a precision amount of 1 millimeter play there to take those measurements, right? So these are some of the probe assemblies. You're seeing some blunt ends type D, for example, that's a 0.23 millimeters diameter, and you are looking at a particular 90-degree angle at the top, that's how the curvature of the blunt end is. If you have much less than that, then basically it becomes more sharp and sharp, and it can possibly penetrate, because but you don't want the probe to penetrate, you just want the probe to kind of sit there and take the measurement, right? There are other probes like 0.33 millimeters. You're looking at 20 degrees, so pretty sharp tip probe, right? These are some examples on the left, and then on the right you're looking at a 3D bioprinter. So 3D bioprinters are getting very popular, where a lot of research groups all around the world, also in India, like they're claiming different forms of bioprinting of scaffolds, tissue scaffolds, and they're able to re-engineer certain tissue properties. But mechanical properties, are they able to? As far as my opinion is concerned, majority of them are not able to, because these scaffolds or very small tissue blocks are usually not very mechanically strong. Then, so if you're saying this is a engineered tissue engineered skin, it is not exactly like skin in terms of mechanical properties. It may have different properties of skin, such as hydration or how the fibers should be assembled. Many of the things would be similar, but the mechanical properties may not be similar, right? So in this picture on the right, you're basically looking at a 3D printed or a 3D bioprinted tissue, or in certain cases it could be the actual tissue which has been extracted from a cadaver or an animal model, and it is poked, it is basically probed, I would say, with the probe of an indenter. And while you're doing this, you're looking at it's within a vessel or a beaker, and while you're doing this precision measurement, this fixture makes sure there is no vibration. It is exactly 1 millimeters, and it is high precision. This was the fixture I was talking about, right? So this could be either bioprinted tissue, or it could also be the real tissue which has been extracted from the cadaver that's being tested, right? So this is another example of the in vivo indentation test. The next type is in vivo imaging tests. These are not plenty, but just a few imaging tests have been fairly popular for in vivo testing. And in vivo, like I mentioned again, it's usually done on live human or animal models. So the first and very popular technique is known as magnetic resonance elastography, okay, or a MRE. It is a technology that combines MRI, which is magnetic resonance imaging, with low frequency vibrations to create a visual map, or they sometimes call it as an elastogram, that shows stiffness of the body tissues, right? So what this does is you are basically taken within an MRI machine, right? And the MRI waves, low frequency vibration waves are created, and based on that, the tissue properties are kind of, the response to those vibration waves are kind of taken into account through the different imaging modalities which are involved. And this is a plot which you see on the bottom. And parallelly, you can have a similar tissue block where you apply the similar vibration, and you are trying to mimic a tissue, what you're seeing in part A. Part B is a real test, and part A is a simulant which is being developed around it, right? So part C is where you're looking at the force versus time. Just look at the force units, it's millinewtons, fairly small, right? And with time, you're looking at some of the force values. Then you are basically trying to get the experimental data, and you want to fit it with some simulant based data by the fitting curve, right? So that's the purpose here, but the amount of force here applied is very low. So again, this description of the mechanical properties of the tissue may not hold ground when you're looking at high impact conditions, or conditions involving a lot of loading on the soft tissues, right? And on the right side, on D part, you're looking at the soft tissue responses to different frequencies of vibrations, right? You're looking at a 50 hertz, 60 hertz, 70 hertz, and up till 100 hertz, right? So when you have a very high frequency, that means the vibration is going very quickly. You do not see a lot of different elastographic like measurements but in a 50 hertz you're looking at a much more optimal one. So every tissue vibrates or has a kind of vibration response to different kinds of frequencies, so that has to be optimized while doing this magnetic resonance elastography, right? So this has become fairly popular technique, and uh, quite a few tissue measurements have been reported using this technique, but the validity of them for real life problems may be limited, right? Okay, the next one is also a very popular imaging test which is widely conducted in the area of biology, biotechnology, and biological sciences, not that much into industrial levels. This is known as atomic force microscopy. Atomic is you're looking at a very atomic level, like really lower scale level. This is able to both sense and apply force at the nanoscales. You're looking at nano level. It's not anymore into micro levels. You're looking at really the nano levels, right? With sub nano Newtonian sensitivity represents an enabling technology and crucial experimental tool in biophysics and biomechanics, right? In AFM, this is widely known as AFM, an elastic cantilever with an intrinsic spring constant K in the range of, this is typically the mechanics of materials. So you have any spring, it has a spring constant basically, which describes how the spring is going to behave, whether it is a very easy loose spring or a hard spring kind of thing. And both a force sensor and a force transducer, right? Sensor is measuring the forces. So basically you have some laser beams, and based on that there are some cantilever movements, and these very not even micro nanoscale movements track what is the property of the material, tissue property at that level. So if you're looking at the figure on the right, you're looking at a force versus d, which is micrometers. From a mechanics standpoint, the forces are increasing. You have a very similar looking plot as you would see in the soft tissue in the macro scale. The properties keep on going up non-linearly when you increase the force, right? From a glycolax and mechanics model, you're again looking at the similar trend. From a sample standpoint, at a 10 micrometers, you're looking at the sample poking and how the picture measurements or the color maps would look like in terms of where the forces are highly concentrated versus where they're not that highly concentrated, right? So this is again a nanoscale kind of technique widely used in the areas of biology, but not widely accepted like when you're looking at like making big scale implants or models which are of macro scale, may not hold ground, so they have to be compared apple to apple, right? So this is another very popular technique. Next we go to what we would really call as mechanical testing methods. Majority of the other techniques in vivo may or may not be considered, except the indentation, as mechanical testing methods which are macro scale. So let us look at some of the macro scale techniques. So the mechanical behavior of a material reflects the relationship between its response or deformation to an applied load or force. This is nice to revisit what a mechanical behavior or a mechanical characteristics actually means, right? It is a response or deformation or change due to an applied load or force, right? The key mechanical design properties are stiffness, strength, hardness, ductility, toughness. All of these terms may be used pretty interchangeably in the industry, but they have different meanings. The first one, stiffness. Stiffness is known as resistance to deformation. So, if I am going to basically push a person, that person doesn't want to get pushed, uh, right? Like that's the resistance to deformation. So that's the stiffness of that person. So very similar to a soft tissue. If I try to push a soft tissue or pull a soft tissue, it resists that due to its elastic behavior, like you would say in a rubber band. So that resistance is known as the stiffness. It is given by the modulus of elasticity. Typically for hard materials and for nonlinear materials, it can have a range of modulus of elasticity, and typically described by the stress strain profile, right? Strength is the maximum amount of load a particular um, soft tissue or specimen can bear. So if I say like I'm working out in the gym and this is the maximum amount of load, or like some big amount of load which I can really pick up, so that is my strength. That is, or this I can pick up a 60 kilo weight, something. So that is my maximum strength. I cannot be picking anything more. So strength is the maximum limit of any material. Hardness is typically how hard is this material, like this has a little bit different meaning than the stiffness and strength. So this basically means like as in terms of a area, what is the maximum amount of hardness or complete resistance it offers. So we are going to explain this more. Ductility is ductility is a property of a material which allows it to be drawn into wires. That's typically what you will see. So it's highly deformable and flowable. Toughness is how tough a material is to impacts, right? So a lot of these terms you will come across quite a bit, like when you are talking about mechanical properties, but many of them hold ground in area of soft tissues, many of them do not. So overall, the mechanical properties of materials are ascertained by performing carefully designed laboratory experiments, right, that replicate as nearly as possible to the service conditions or the real conditions. And this becomes extremely complex when you're looking at soft tissues, right, because soft tissues do not get loaded in uniaxial loading or biaxial loading usually. You could have impact loadings, you could have an injury scenario which is multi-axial loadings coming from different parts. Also the structures of the soft tissues are very, very unique, like the nasal cavity has a unique shape. So if there was an impact from here versus here, it's going to behave very differently, right? So it's not only the material property, it's also the structure. But having said that, this is a very new arena of research, and that's one of the key purpose of this course, to kind of introduce you to all the different soft tissue characterization modalities, what soft tissues are, how they can be used in different sorts of models which are upcoming. And this will give you a clear insight of what research areas you can target, or what target areas you could possibly venture into in terms of products and services, right? So let's take a look at the map of the mechanical tests. These are all the in vitro ones which we are talking about. In vitro is something which you are conducting on a sample, right? So first kind is known as static. Static is when you do some kind of an experiment, like for just one instance, like you have one drop or one instance, you pull something and that's the measurement you are taking. So majority of the static, or you sometimes call it quasi static. Quasi static is like something is which is moving at a very slow strain rate. You're doing tensile test, compression test, bending and torsion. These are the four most popular testing methods which are there in terms of in vitro mechanical tests. Next is dynamic. Dynamic is where you have a very high strain rate, or very quickly moving, quickly deforming clamp, which is causing a lot of either vibrations or loads on the soft tissue. So there you're looking at fatigue and resonance, right? Resonance is because of the vibrations, right? So these are the wide variety of in vitro tests which are conducted. There are few more like shear and others which we will talk about at length in a different session. So the first question here is, in terms of in vitro mechanical tests, why do you need material testing or mechanical testing of the materials in the first place? This is a good question to revisit every now and then, because then we realize from different perspectives why testing is important. So to test mechanical properties like ultimate tensile strength, yield strength, elongation, toughness, etc., which is a design input, right? So many of these soft tissues, if we are trying to work in the area of engineering of soft tissues, tissue engineering, or you're trying to build a simulant, you're trying to understand the properties of an actual tissue, whether that has gone bad, whether you're testing on cadaver, you want to make sure that this cadaveric tissue is performing how exactly it would perform in a live human, right? So these kind of things could only be understood if you know the right mechanical properties. Even if you are a doctor, you're trying to do some robotic surgery in a certain place, right? what is the right amount of load, or what are the right amounts of cutting forces which are required, right amount of suture forces which are required. These are quite unknown quantities. A doctor doesn't understand the biomechanics of the problem. So that's where understanding the mechanical properties of the native tissue or the live tissue or the real tissue and how it compares with the possible diseased or injured tissue is of value, right? So also with the knowledge of material testing, you will be able to make informed choices in using several raw materials, like whether I would like to use hydrogels for mimicking the skin tissue, or whether I would use silicone or some other materials, right? To check the properties of a material after heat treatment welding, this doesn't apply for majority of the soft tissues, brazing and other operations. This is for majority of the hard materials, right? Ensure batch and production quality. So this is when I'm making soft tissue mimics, it's nice to see whether the first mimic of the skin is the same as the second mimic and things like that, right? So as a part of maintenance and to prevent failure in usage, also when you're building implants and biomaterials, so what is an implant or a biomaterial trying to do? They're basically trying to mimic the real property of the tissue which is either lost due to a disease or an injury, right? So if I have an hip implant, then basically what I'm trying to achieve with that implant is the lost function, where there's a hip failure, or there was a breakage in the hip, or like the ball and socket joint of the hip did not work, so I wanted to place an implant, right? So the implant has to be able to bear all the loads of the actual tissue, or it's an ACL tear, right? Cartilage tear. There also you're trying to look at the load bearing properties. As we delve more and more deeper into this course, what we will learn is it is not only the mechanical property of a small sample, but it is the mechanical property of the overall structure which we can study through advanced experimental techniques as well as advanced computational modeling. And we are going to take glimpses of that, like using through various learnings of the softwares and the techniques, right, through this course. So stay tuned for that. Let's come back to the types of material testing. The first type broadly is known as destructive testing, where the material is physically tested to destruction or indentation, right? So if you indent something almost permanently, then you are kind of destructing a surface part, right? Or if you're pulling a soft tissue beyond its limit, it's going to break. You cannot restart the test from there, right? And most of the destructive testings are done to measure the strength, hardness, and toughness, right? Through an impact, you want to learn how tough this is. Through a static or a quasi-static pulling, you want to know how much is the strength and things like that. You also want to look at the hardness, right? Examples are tensile test, impact test, and hardness test. I'm going to explain all of these tests as we go along. Next type comes the non-destructive tests. So samples of finished products are tested without spoiling the product. So this is for biomaterials or implants. Let's say I have a nice absorbable stent which is going to go inside a particular artery, and I'm supposed to be testing this mechanically to those conditions where it will be within that artery, right? Excuse me. थोड़ा काट दीजिए, sorry. Within that artery, right? So this is how we are going to look at the mechanical tests of like not only the soft tissues itself, but the implants or materials which interacts with those soft tissues, right? So then sometimes with a lot of different finished products like the footwear insoles, I am supposed to be looking at foot conditions where I have a foot pain due to some plantar fasciitis condition. I want to have a support insole. So how do you test that? If you do not want to destroy that insole, you just want to test it to that point that it is able to function rightly. So those are known as non-destructive testings, right? Some techniques such as radiography, dye penetration tests, these are sometimes also used for non-destructive testing. Also, tensile and compressive tests can be non-destructive. They do not have to be carried forward till the ultimate point when it breaks, or when you push that it completely crushes, right? So destructive and non-destructive has a thin line. You can do non-destructive tests even with the machines which are where you can perform destructive tests depending on the load limits and other things, and you have some other techniques as well which you can implement, right? So this is broader reasons for doing material testing again. So typically what you get out of a material test is a very important thing, and we want to revisit this a few times just to make sure this is very, very clear. So the major reason why you do a material testing or a soft tissue testing is to understand the stress versus strain response. This is the response we are going to talk about a lot, and we had explained I'd explained quite a bit like in the previous sessions, where you basically get a load versus deformation data out of an experiment. Either you do a tensile testing experiment or a compressive testing experiment, and you use that data to generate a stress versus strain profile. Just to revisit, what happens is when you pull a specimen, you are applying displacements. You're basically applying a load which is causing a displacement. Load is in newtons, displacement is in millimeters, and load divided by the original initial area will give you the stress value. So you get a lot of points of stress, and the displacement which is occurring due to the changing load divided by the initial length of the specimen. This length, by the way, I should point out, this is from clamp to clamp. So you do not consider the length which is embedded within the clamp. So let's say the total specimen length is 10 centimeters, but the clamp is taking up 2 centimeters here and the bottom clamp 2 centimeters here. So you're basically left with 6. So 6 is the length, 6 centimeters, right? So that will give you the strain. When these are noted at various points, as you are keeping on increasing the loads, the displacements will also keep on increasing, and so the stresses and strains. And this is what you would like to plot in a stress strain diagram, right? So stress strain diagram is of absolute importance, like while we do mechanical testing, and this is what we are going to repeat quite a bit. Whether you find modulus of elasticity or you use some curve fitting techniques, that is separate, like that comes much more later. But what you need as a primary raw material for mechanical testing is the stress strain profile, right? That is the major thing from which you can analyze different activities. Just like it's a resume of any kind of sample, like we have resumes for people, it's like the resumes for any sample. You can only detect how the sample behaves mechanically by the stress strain profile. And this is a common example of the stress strain profile design where you're looking at a UTM or a universal testing machine. Okay, this is another reason why material testing is required or soft tissue testing is required. Historically, from the Stone Age to the different Bronze Age, and you have different kinds of Iron Age and different ages, every age or every tenure in the history of time has been located or represented by the different kinds of materials which have been discovered during that time, right? So there was a time in which iron was discovered, that was the Iron Age. There was a time bronze was discovered, Bronze Age. So that's why materials hold a lot of importance in the overall scheme of things of what we are trying to achieve in a day-to-day life, be it products or different kinds of diagnosis or treatment modalities. So everything which you use, from a surgical needle to different aspects which comes with like an operation bench or different ergonomical activities or different products, that all comes in touch with the tissue. They have some material reference, right? So that's why understanding the material is very important, and that allows you to create biomaterials, implants, and other technologies alongside, right? So here is an example of the impact test, how it got popular, and this was much later than the regular tensile or the compression test. Here the hammer strikes the face that is opposite face with the notch, and the energy absorbed by the specimen is determined precisely by measuring the decrease in kinetic energy, right? Like, so potential energy, kinetic energy. So when an impactor hits something, very similar when a ballistic hits me, or I get hit by something, like let's say I push my face towards a door or something happens in an injury. These are all transfer of energy. So how that transfer of energy is causing deformations and changes in the stress strain, This is of importance in an impact test, right? So let's revisit all the different kinds of tests, and now we have understood why mechanical tests of materials and tissues in general are important. So let's revisit our first test, and let's get a little bit into the depth of how different tests are conducted. The first one is known as tensile test, right? So here what happens is, typically you take a specimen, and like I had mentioned, majority of the specimens for hard materials are in the form of a dog bone shape. Dog bone has a narrow kind of like cylinder, followed by two bulge cylinders or a bigger cross section cylinders on the side. That's known as a dog bone shape, but that's quite not possible with a lot of soft tissues, so you can just go with a rectangular shape, right? So here you're looking at the different diameters, radius, and how dog bones are defined, like in terms of specimen. The specimen sizing is very important. So a standard tensile specimen with a circular cross section is very popular, but when you take soft tissues, it will usually have a flat cross section or a rectangular cross section, right? So then basically you place it within a set of clamps within a tensile testing machine. There is a load cell at the very top. Let's take a look at the figure on the right, and you are looking at another part which is known as the extensometer. Extensometer is sometimes used to take a look at the displacements, but the displacements, what the tissue, how much the tissue is displacing, can also be calculated by looking at how much the crosshead or the gear of the entire assembly of the UTM is moving. So if this is moving by, let's say, some 360-degree 5 times, so you know the pitch of the screw, so this is how much it is displacing, and you can easily back calculate how much the displacement is. That is typically how it is done. So extensometers are not that widely used. So you have a moving cross section with certain screws which takes the platform up and down and causes the displacement, and the load cell keeps on measuring the loads, and finally what you get is load versus displacement data, or load versus elongation data. This is plotted and studied. Variables such as strain, stress, elasticity, tensile strength, ductility, and shear strength are measured and computed. So many different quantities can all be computed from just the force versus displacement data, dynamic data, which has been converted to stress and strain, right? The test specimen, like I've mentioned, can be round or flat, and the right picture basically shows you a schematic representation of the apparatus which is used to conduct tensile stress strain tests, right? Okay, further into the tensile tests, we had talked about some of the biaxial tests. So the procedure basically involves grasping the sample's ends with fixtures and pushing it apart until it fails or reaches a specific strain, right? And that is more of a destructive kind, but you can still pull it to a certain extent, like where you do not want to take it beyond destruction. It can come back to its original form. That can also be done. So here are some pictures to look at of a biaxial testing machine on the top, and it is testing on some tissue mesh, right? So there can be skin graft mesh or some graft kind of tissue, right? And it is also looking at some of the localized strains and stresses which are developed. This is using some imaging techniques such as digital image correlation. I'm going to take one or two sessions where I speak at length about digital image correlation. It's a very interesting technique of measuring soft tissue property during an experiment, and you can use this data to compare with simulations or computation. So I'm going to explain digital image correlation at a later stage. It involves a little bit more attention than this, right? So the sample's stress resulting from the external load is determined using the sample's cross sectional area and the tensile force applied to it, right? During uniaxial tensile testing, the tissue can be stretched while the unconfined edges can contract, right? And the fibers can be crushed in the lateral direction. Biaxial testing, tensile testing, which eliminates fiber compression and more accurately simulates the in situ loading of fibrous tissues, can however overcome it. So biaxial will give a much more realistic view of testing of a lot of soft tissues, which are majority of the soft tissues are under biaxial loading. If I take an abdominal tissue which can get a hernia, right, that is also subjected to biaxial strains, right, or biaxial deformation or biaxial loading, right? None of the tissues in the human body has a uniaxial loading component. That's why sometimes biaxial is considered as a better standard. but not always the biaxial devices are available. So that's why uniaxials also do suffice. You can take uniaxial around this and around this, right? Like that will give you some properties. So this set of figures are basically showing you on the right the biaxial testing of a human adipose tissue and its strain contour mapping. So this is what you're looking at from the right side. Okay, further into the tensile testing system, this is how a much more professional tensile testing system. This is from Instron. It's a very popular, like manufacturer which makes some of the high precision universal tensile testing machines. Here you're looking at very sophisticated grips, or clamps, or the top and bottom, which is specifically made for soft tissue clamping, and has very high precision kind of clamping techniques, and just to make sure the tissue is not overstressed, understressed, and it doesn't break, right? On the right side you can see the stress strain plot, which is which is dynamically noted, and you can take this data out also. The red switch on the bottom next to the yellow is a kill switch. So if at some point if the clamps go off limits, then you can hit the kill switch and the test will automatically stop. Another thing to note is any kind of tests, be it tensile, compression, or the other tests which we are going to discuss, have to be conducted at least 3 times. If they are not repeated 3 times not necessarily on the same specimen. If you have taken it up to destruction, you cannot be using the same specimen. Take another sample of it. Take 3 different samples. Then you can overall say that the kidney tissue properties are this, with an error bar of this, right? Or set of error bars. If you are not taking it up till destruction, you may be able to perform some repeatability tests on the same specimen. For soft materials such as silicon based or hydrogel based materials, if you are not taking them to destruction, you can test them quite a few times, right? Okay, this is this picture is basically showing the measurements of a rupture. So this is on a hard material, but even in a soft material you want to measure using, this is known as a vernier caliper, which is a high precision scale or a ruler, from which you are basically measuring how the particular specimen of the tissue or the material has fractured or ruptured, what is the way of rupture. All these things are very, very important in the area of soft tissue mechanics, right? If this is having a curvature in the rupture, or it's a straight cut, these kind of things depict a lot about how this tissue is going to break, and has a lot of implication into studying forensics and surgeries. Like in forensic medicine also, if there is certain cut or a certain wound, you can very clearly identify what could have been the possible injury mechanism to cause that wound. Area of ballistics also very, very much the same, right? Or there is a particular wound which you want to surgically improve or surgically correct. You want to know like what are the right techniques. There also the fracture or the rupture component is very important. So this picture is showing just the measurement of the fracture or the rupture. Further into the tensile test, this shows the overall picture of another machine, which is a high precision machine. You can very well see the clamps here, and you can see a tensile test specimen which is being pulled. There is a contraction which happens in between, and that is due to the Poisson's effect. Poisson's ratio I would like to introduce is a very important quantity besides modulus of elasticity, which we are going to talk about quite a bit at length. It is known mathematically as lateral strain by longitudinal strain. What is lateral strain? Lateral strain is along vertical to the axis. Longitudinal is towards the direction of the axis or towards the length of a specimen. Longitudinal strain is nothing but the overall displacement at a particular location while you are holding this. So Poisson's ratio also may change a little bit depending on where you are holding this. So let's say at a particular instant, time is equal to t is equal to 31 seconds. You are looking at the overall specimen length of, let's say, 50 centimeters, and the original length was, let's say, 30 centimeters. So the displacement has been 20 centimeters. So 20 divided by 30 will give you the lateral strain, the longitudinal strain, sorry. And the lateral strain is the initial cross sectional width divided by in the denominator, and in the numerator it will be the final cross sectional width, right? So the change in the cross sectional width. So let's say the initial cross section was 1 centimeters. Now this has become, at this t equal to 31 seconds, let's say 0.6 centimeters, right? So 1 minus 0.6 is 0.4. 0.4 divided by 1 centimeters will give you the lateral strain. So lateral strain divided by the longitudinal strain will give you the Poisson's ratio. It cannot exceed 0.5 due to mathematical limits, but usually you would see Poisson's ratio in the order of between 0 to 0.5, right? Poisson's ratio, a high Poisson's ratio number means that it is going to have more contraction, versus a low Poisson's ratio means it will have less contraction when you apply the same amount of pulling, right? So harder materials, less elastic materials will have less contraction, right? But very highly elastic material will have a high contraction. So this is what you're looking at in this tensile test, right? Due to the pulling force. And on the right side, it is very clear, it's a dynamic test, so it keeps on pulling at a certain displacement or a strain rate. The next test is a compression test. हमारे पास टाइम है कितना? 46। अच्छा अच्छा, मुझे लगा समय हुआ, आप थोड़ा उठ रहे थे, मुझे लगा ठीक है, मैं इधर से कंटिन्यू करता हूँ. So the next test here is a compression test. This is very similar to a tensile test, just the reverse of that. So another common characterization method, this is like, which is similar to tensile, except that the sample is compressed rather than stretched under tension, right? So here basically you are using the same universal testing machine, the only difference here being that you are having different kind of grips or clamps. The same clamps cannot be used which you used for doing the tensile test. Here you are having like a flat compression grips, right? So even in our universal testing machine, we are having similar kinds of grips which can force the tissue within it, like kind of have a sandwich for the tissue and keep on applying loads, right? The bottom clamp is usually fixed, right, and the top one moves. But how much can it move? There can be certain limits which are set, because certain soft tissues like the brain tissue, if this is the bottom clamp and this is the top clamp, it can very easily get crushed and the clamps can collapse against each other. So that's why you want to make certain limits that the clamp should automatically stop, which is when it has come, let's say 2.5 or 3 millimeters within this vicinity or something like that, right? Just to make sure these kind of tests do not lead to a damage of the machine. So it has the same fundamentals of a tensile testing premise, measuring the force applied to the sample to determine its stress. So the measurement quantities are very similar. You are looking at, you are applying a force that is causing some compressive displacement. Force versus the initial area, right, will give you the stress in different points because the force is changing, and the final depth or the compression amount, the, let's say the initial delta something compression, delta d or something, divided by the initial depth or initial height of the specimen will give you the strain. So stress versus strain is again plot through force versus displacement data. The stress strain curves are created by continuously recording the sample stress and strain. However, the sample is positioned between the two flat plates for compressive loading rather than being grasped, right? So that I've already explained. So some of the compression tests of very soft materials and very like materials which are going to deform when you apply a little bit of load only, have to have very unique fixtures, or they need to have unique load cells. Very similar theory, just the way of doing it is opposite to the tensile, right? So the figure on the top here is showing the compression of porcine and human aorta tissue. So you can see some, like an extra grip kind of in this. So you see the compression grips on the top, and between that you see another cylinder. So that is to apply the load only in the place where the tissue is. If you're applying a load overall on top of a bigger surface and the tissue is covering this much surface, applying this much is not good. So sometimes you need to have additional fixtures to apply the compressive load correctly to the exact tissue area of interest. This is of very important point to note. You should not just take the big clamps and place a small piece of soft tissue and totally put the compressive loads, right? You have to know that this is the area of the tissue I'm trying to study. So let me put another cylinder which is kind of a attachment which is along with this compression, and this compression like clamp on the top, flat clamp, is going to apply the load to the small cylinder, which is going to further apply the load to this tissue. Okay, so the next one is a shear compression device including an undeformed sample. So shear anywhere basically means when there is a sample and I'm going to pull that sample from one end on the top and pull that sample from one end of the bottom, or fix the sample from the bottom, pull it from one. So when there is layer by layer kind of pulling, so you're not pulling the entire sample together, you're pulling one tip of it and the other tip is fixed. That is the shear loading, right? Be it for tensile or compression. If when you are there is this entire specimen and you are forcing just the compression clamp on one end of the soft tissue, that means it's a shear compressive loading. So many of the soft tissues undergo shear compressive loading. One example is in the uh, digestive or the stomach system, like many of the organs are not getting entirely compressed by the attachment or the nearby soft tissues. They may have a small portion which is compressing the other. In the female pelvic system, the urinary bladder and the rectum is getting compressed, uh, is sandwiching the uterus, and basically the compression is at certain locations only. It's not that the uterus, when it is growing during the childbirth, it is entirely compressing the bladder. It's compressing it at certain locations. So that's a shear compression kind of loading in certain places, and this can cause different mechanical responses, right? So here is an example on the bottom where you're looking at a shear compression test device, and many of these devices or fixtures you can build using 3D printing or machining operations, where you need to apply a certain kind of loading at a certain point of interest, and you do not want to use a basic equipment of a UTM, right? So there is a plunger, there is a black panel, front panel, tissue sample which is in between, outlet channel, bottom panel. So you are trying to look at a shear loading on the tissue. When the tissue is placed like this is shear loading, right? Not the entire tissue is getting compressed, right? So then you are basically trying to look at the overall size of the tissue and how much of that is subjected to the loading, and finally conduct the shear forces or the shear response. You record the same, right? So having said that, what I would like to point out is, it is not only that you take a sample of the tissue and basically place it within a universal testing machine and your entire test is good to go or your results are fine. You have to look at the actual biomechanics of the system, what is happening in the system. So if I am trying to look at the human foot, the compression of the human foot, is it the entire foot I am applying the load to during walking? Not really. During the walking there is this heel strike, then there is this complete foot loading, and there is this toe off phase. Let's say there is an injury which happens during the toe off phase. This is an ankle injury, right? So if I want to study this particular soft tissue, I want to only apply loading at the forefoot or the front of the foot, right, during the toe off phase. I do not want to apply the whole loading on the foot and understand ankle injury, right? This is also a compression testing problem. So I have to understand the problem very clearly, what the constraints of that problem are, and also what are loadings and how those loadings are applied. That is very key. So I should not just take a foot model and place it within a compression bench in a UTM and just say, oh, this is the property, this is how it is going to go. I should be as accurate as possible to use the right foot structure and place it in the right way so that the right amount of loading can be placed. These are known as multi-axial or much more advanced loading operations, right? You can do it through making fixtures and other kinds of attachments which can be placed along with a UTM. We do that very often in our lab. This is an example of a compression test where this person is basically trying to put a specimen. It's a soft foam which is similar to a tissue material. It is placed between two completely flat clamps, and that is going to give him quite a bit of good information in terms of stress versus strain, right? This is another example of compression test using the Instron machine which I was just referring to. So within this, you're first of all learning on the left side a compression test with flat grips on a spring. Uh, this could be very similar to a spinal cord and various other bone type tests which are conducted. On the right side, you're looking at a compression test on a footwear. So I had just spoken about a footwear. You're trying to look at how this footwear is going to behave in terms of properties, or whether it is going to take that much amount of compression loading where a person of 100 kilograms is standing on that footwear. You want to test that as a product, right? So all these understandings and studies which we are doing as a part of this course are directed towards building the next generation of the products or surgical techniques or methods in which all the doctors, biotechnologists and engineers can be helped. These are not only for characterization and studies. This is the ultimate goal of building products and techniques. So this is one of the product where the shoe is being tested to look at whether a 60 kilogram versus a 100 kilogram, when the load is applied at different strain rates while he's walking or running, is the shoe will be able to bear this or not, right? So this is another example of the compression test. So with this, I think we are going to pick it up from here in the next session and talk more at length about several other mechanical testing methods, and also take quite a few live examples of some of the soft tissue testing. So stay tuned. I'll see you again shortly. Thank you.